So today is an application day. And as a reminder, we've done a couple of applications. We've talked about things such as mixing, where we have maybe a tank and we have salt water coming in. Of course, it doesn't have to be salt, but the nice thing is it's pretty harmless as things go. We don't have a lot of problems about you're mixing cyanide in your wine glass, you know. We feel like that's not a way to really motivate math, so we try to avoid those types of problems. Salt and water, harmless. We talked about population models, so things like logistic equation, exponential growth, exponential decay, and so this is sort of our third big application in some sense, which is oscillations and springs. And it takes us back to our very first day when we talked about springs. And so we're going to talk about essentially one extra component that we didn't have on our first day. So we're going to talk about spring mass systems. And sometimes we'll see the word dashpot, which I don't think is a very common word. I like the word damper because that's a little bit better descriptor. And so the idea here is we have some mass and it's attached to two objects. So one of them is a spring. And we talked on the very first day that springs have this beautiful fact called Hooke's law, where when you stretch a spring, there's sort of a force pulling you back. And it's proportional to how far you've pulled. So the farther you pull the spring down, the larger the force that the spring will exert to pull it back in the direction to where it considers sort of neutral. And so that's where the K is proportional. The X says how far you've pulled, and the minus sign just says, look, if I pull it in the positive direction, it wants to pull it back in the negative direction. So it wants to go in the opposite direction of the sign of X. So that's that force acting on our object. Now we're going to introduce a second force. This is the damper. I guess you could call it the dashpot. I'm not sure why we call it the dashpot. But here, it has a slightly different behavior. So it turns out that in this particular construct, it doesn't matter how far you've pulled. What matters is how fast you're going. So you can imagine, if you will, sort of say, you're sort of the object, and I like to somehow think of this like you have this paddle in here inside this chamber which contains something. All right. And now it doesn't matter where you're at. The question is, how fast are you trying to push it down? The harder, the faster you try to push it down, well, it's harder because, somehow there's a little bit of give. And so it turns out that the force is not going to depend on whether you're pushing near the top or whether you're pushing near the bottom, but rather how fast you're pushing. I don't know if you've ever seen these videos of these, what they call non-Newtonian fluids, where it's like, if you try to push really hard or punch it, it hurts because it fights back a little bit. But if you go slowly, it's like, no problem. Well, that's kind of the idea. If you go slowly, fine. It doesn't really push too much. But if you try to go quickly, whoa, a lot of resistance. So for the damper, it doesn't depend on your location, it depends on your velocity. Again, there's a proportional thing. So that's why you see something x prime. All right, so what do we have? Well, we put it together. We have the force, well, that's mass times acceleration, mx double prime, and we sum up. Well, we have the spring acting, and we have the damper acting, and then we might have some external force. Or, if we put it together, we get mx double prime plus cx prime, because we move it across, plus kx, move it across, equals some function, which is the external part. So that's it. That's the setup. And so now when you look at this and say, oh, this is nice. What are some things that are nice about this? Well, what's the order? Second order. Yeah, that's not too bad. Are there other things that are nice here? Constant coefficient, yeah. The MCK. Oh, we like constant coefficient. Anything else? It's linear. Oh, we like linear. Like this is our sweet spot. Constant coefficient, linear. Ah, perfect. And oftentimes there's no external force. So oftentimes it's homogeneous. So what do you do in these problems? Well, you work to identify what is your value of MCK, check to see if there's anything external, and then you solve. So there's not much to it, really. Once you get past the setup, it's what we've done before. All right, so are we ready to try a problem? All right, good. We'll do a problem then. Here we go. So, analyze a spring mass system with no external forces. Woohoo! No external forces, good. And it gives us our coefficients. So m equals 12, m equals 2, c equals 12, k equals 50. And then we just have to remember what everything is. And then it says, hey, there's some initial conditions. So x0, which is determined as x not equals 0. So that's x0 is our position. So it starts in the neutral position. However, x prime is 0, which we could also call the initial velocity. So v0 is -8. So it might be starting in the initial neutral position, but it has a little bit of speed to it. So, all right, well, let's see. So first thing we should do is write down the equation. Well, so since it's a spring mass system, we know it has the form mx double prime plus cx prime plus kx equals 0. That's just our generic form. And now we have to think, what are the values of m, c, and k? Well, can we figure it out from this problem? Yeah, this one's pretty nice. It tells us. Sometimes it doesn't tell us. We got to think a little bit, but oh, okay, if you're going to give it to us, we won't fight you. We'll just accept it. We are happy that you tell us. All right. Good. What can we do now? Ooh, the mysterious, what do we do? Yeah, we can turn to polynomials. Now, before we turn to polynomials, is there anything we can do to simplify this? Yeah, let's go ahead and just get rid of the common factor. Divide out by 2. Might as well. I like getting rid of common factors. Okay, so now this is constant coefficient, linear, homogeneous, our favorite kind of differential equation, because we can take this into a differential equation problem and turn it into a algebra problem. Yes, and of course we love algebra. And what's the algebra problem that we get to solve? R squared 6r plus 25 equals 0. Ah, algebra. Algebra, yeah. Okay, so does this factor? Someone's really no. And then there's a lot of Okay, if it doesn't factor, what can we do? Do we just give up? No! We never give up. We are after all the points. You got to get them all. All right. So, we're not giving up. What's next after we say we're not giving up? Yeah, quadratic formula. All right. So, R equals, how does it go? Negative b plus minus square root b squared minus 4ac. Oh, you guys are good. All over 2a. Okay. Well, 4 times 1 times 25 is 100. 36 subtract 100. Negative 64. There's a negative inside that square root. I think things might be getting a little bit complex. All right, but negative 6 over 2 is negative 3. What happens to the square root of negative 64? 8i. So when you see a square root of a negative, that means I is involved. Now, there's an also over 2, so 8 over 2 becomes 4. So we have negative 3 plus minus 4i. All right. Now, I will say when it comes to springs, it's not that unusual to see complex roots. It's not a requirement, but it's not unusual. Because when we see complex roots as solutions to these kinds of equations, what does it mean that our, going back to our differential equation, what's going to be showing up? Sines and cosines show up. Sines and cosines are things that oscillate. What else oscillates? Springs oscillate. Okay, so it's not that unusual to see complex roots when you do these spring mass systems. All right, great. So we've solved our algebra problem. Now we go and say, all right, we've got to translate that into what does it mean for our differential equation? Well, it means that we have, well, we're going to have two solutions, A times something plus B times something. But what are the pieces? What goes into these slots? Do you remember? Yeah, so there's going to be like negative 3 is the real part. This goes into the exponential part. And then the complex part, this goes into the sine/cosine part. Okay, so it would be e to the, now we have to be careful here. We shouldn't use x because x represents where the spring is, so we'll use t. So e to the minus 3t, it doesn't matter which one comes first, cosine or sine. Cosine 4t, e to the minus 3t, sine of 4t. All right, so there's our generic solution. All solutions to this spring mass system have this form. Are we done? No. Yeah, that's right. It's like they say, but wait, there's more. What's the more? Initial conditions. Yeah, we were told something about what's going on. All right. Well, let's start with the initial condition, x of 0 equals 0. So we plug in x0. Okay, that equals 0, because I'm just reading it off here. When we plug 0 into this first piece, e to the minus 3t cosine 4t, what comes out? So e to the 0 is 1, cosine 0 is 1, so the whole thing is 1 times a is a. When we plug 0 into the second part, what comes out? 0. So can we use that to solve for anything? Yeah, we get a equals 0. Well, that was quick. So that says that our solution looks like b e to the minus 3t sine 4t. But we haven't used our second condition yet. All right, for our second condition, we need to take our derivative. And since we've already knocked out the first part, we just have to take the derivative of the second part. All right, so x prime of t, I'm just going to emphasize, we're not evaluating yet, we're just taking our derivative. What's our rule for taking the derivative of e to the minus 3t sine 4t? Product rule, good, good. Okay, the derivative of e to the minus 3t is what? Yeah, minus 3 comes down. So, all right, this is minus 3 times b, e to the minus 3t sine of 4t. The derivative of sine of 4t. 4 cosine 4t or negative 4 cosine 4t? Are you sure? Yeah, because you're right. It's a positive. You know, just checking, keeping you honest. 4b e to the minus 3t cosine 4t. And now, plug in our initial conditions. X prime of 0 is equal to negative 8. Well, what happens to the first term? 0. What happens to our second term? 4b. Well, what does that tell us? B equals negative 2. So our answer is minus 2 e to the minus 3t times sine of 4t. And that's our analysis. Now, it doesn't ask us to do this, but what does it look like? Okay. We can actually kind of figure this out. So, sine of 4t does what? Yeah, I can see people moving their hands up, and it goes up and down, no big surprises. Okay, so that's good. So we'll just make a note. This oscillates. Good. So one thing we can think about is to say, well, where is it oscillating between? We can think about it's oscillating between this curve and the negative of that curve. Because sine can go between positive 1 and negative 1. So what you can do is you can say, look, since I know sine oscillates, I'm going to sketch this curve. Now, what happens to this curve as time goes to infinity? It goes to 0. So it starts at negative 2, heads towards 0. The negative of it starts at positive 2, heads towards 0. And then we say, okay, I'm going to oscillate between those two curves. And you might have to think about which way do you start? Well, we know we start at 0. Are we initially going down or up? And how do we know it's down? Yeah, we're going down, but how do we know we're going down? Negative velocity. So what we'll do is we'll just go back and forth. So that's what's going to happen. So that's what the curve is doing. That's what the spring is doing. Kind of like what we think springs normally do, actually. They kind of like, oh, I'm getting tired. All right, I'm just going to peter out. Just stop. Well, never actually really stops. But for all intents and purposes, for our engineers, it stops. So, all right, good. Well, any questions? All right. Well, in that case, you should try one. So, here we go. There's a spring mass system with no external forces. It has m equals 4, c equals 40, and k equals 84. Given that initially x0 is 2 and v0 equals 6, find the solution for the system. Let's find out. So we just repeat the process, right? We know it's a mass spring system. mx double prime, cx prime, kx, no external forces, and because it tells us no external forces. And then we say, all right, well, let's figure out what these coefficients are. And we're like, oh, well, they tell us, so that's nice. So we have 4 and 40 and 84. And of course, we could simplify this by saying, ooh, they all have 4s. So that's like x double prime plus 10x prime plus whatever 84 divided by 4 is. 21, okay, I'll believe you. All right. And we say, great, perfect, our favorite kind of differential equation, because we can do algebra. R squared plus 10r plus 21 equals 0. And does it factor? Yes? How does it factor? Someone has suggested r plus 7 times r plus 3. Maybe. You always check, right? R squared, 3r plus 7r is 10r, and 7 times 3 is 21. Oh, yeah. Cool. So our roots are negative 3 and negative 7. Not complex at all. That's okay. That's okay. We'll talk about why it doesn't have to be complex. But now we say, great. We come up into our differential equation. We say that tells us our solution looks like something e to the minus 3t plus something e to the minus 7t. That's looking pretty promising. Doesn't mean it's right, but it looks like it's promising. Well, we got to now dig in initial conditions. Okay, x0 and v0. Now, v0 we know is just secret code for x prime. So we'll write down x prime. Now you might say, last time you just went right away and evaluated. Well, last time we had an initial condition of 0. That's a great initial condition. Anytime you can get 0, we're lucky. These have pretty simple derivatives. Minus 3a e to the minus 3t minus 7b e to the minus 7t. And now we're going to get our two equations, namely that x of 0 is 2, but that would equal a plus b. X prime of 0 is v0 equals 6. That would be negative 3a minus 7b. And now, two equations, two unknowns. The bread and butter of math. We do this so often. So often. This should become, hopefully, second nature. Well, we just have to think about how can we combine these in a way that gets cancellation. And there's not a right answer. There's oftentimes many right answers. So basically, as a reminder, you have two options here. One is you can do a substitution. In other words, solve for one variable, put it into the other. And the other one is you can do elimination, which is to somehow combine things so that you get cancellation. And I like to eliminate. Do you want to eliminate the A's or the B's? Eliminate the A's? Well, here's 1a and here's negative 3a. And now we're like, well, what can we multiply the equations by so that when we combine them we get 0 A's? So I would say the smart thing would be to multiply the first equation by a 3, because then you'd have 3a and minus 3a. 3 times 2 would be 6. And then add 6 would give us 12. Yes? 3 times b is 3b. 3b subtract 7b is what? Negative 4b. And there's no a's because that's how we set it up. The a's will cancel out. It's 3a and subtract 3a. So what does that say about b? b has to be negative 3. Well, now that you know b, you can come back into the first equation and say, oh, 2 has to equal a minus 3. So what is a? 5. And so you know a, you know b, so you write it down. 5e to the minus 3t minus 3e to the minus 7t, and it works. Beautiful, beautiful. Okay, so you may have gone to a point that maybe you got down here like, darn it, where's my complex stuff? Where's the I? Well, not everything involving a spring has to have an I, because a lot of it depends on what's going on with your damper. The springy part is what makes things want to go up and down. The damper is trying to prevent that. It's sort of like if you've driven a car. There's your shocks and there's your shock absorbers. You know, just one of them, you'd be springing up and down. The other one's trying to say, no, slow down, don't bounce. And depending upon the balance between them, you might see oscillations and you might not. So there's a couple of different types of behavior. So let's talk about them in a nice, friendly chart. So here's essentially all the types of behaviors you might see in a spring mass system if there's no external force. If there's an external force, all bets are off. Lots of weird stuff can happen. And what do? Well, we say, let's look at that auxiliary polynomial And so this, as a reminder, this is coming from your mx double prime plus cx prime plus kx equals 0. And it's just a translation into a polynomial. You're like, all right, well, you have roots of this, and there's some things that might happen. So one thing that might happen is that you have what we would call pure imaginary roots. So plus or minus I times some constant. And these are actually really simple to understand what's going on. This corresponds to undamped. The reason we call it undamped is that this really says that C equals 0. There is no damping going on. And so it's just the spring. So in your spring mass system, you forgot to attach a damper. And so what's going to happen is your solutions are going to become just sines and cosines. And so you'll just keep oscillating the same amount forever and ever. So that's what happens if you don't put on a damper. Then you might say, well, what if I just imagine turning up the damping a little bit? So I'm turning C up just a little bit. We call that underdamped. And you might say, okay, well, what is that? Well, that's when you're going to get complex roots. So you have a little bit of a real part and a little bit of a complex part. So our solutions, when we translate that, e to the minus at cosine bt, e to the minus at sine bt. And so we have something that oscillates, but also is going down. So in other words, you can see that there's this sort of exponential boundary coming in. So it's going back and forth between two things, but they're going together. And we call that underdamped. And then we'll skip over critically damped and come back to it. So underdamped was our first example we worked through. If we have distinct negative roots, so there's no complex parts at all, but they're distinct, well, okay, we know what solutions look like. E to the minus at, e to the minus bt. Of course, when I read this word, it's very scary because it looks like the word debt, but no, it's just math. Nothing to be scared about. We call this overdamped. It's like you installed like super heavy duty shock absorbers. It's like, I am not going to feel the springiness at all. Way too much damping. So that's when C is very large. And then there's this one we skipped over, which we call critically damped. And it's kind of the fine line. It's just enough damping that you don't experience any oscillation, but not too much. And you might say, well, what do you mean by too much? So in some sense, it's a little bit hard to see this without sort of working through a bunch of examples. But the nice thing about being critically damped is in terms of your spring mass system, it's the fastest way to quickly get your spring mass system to go back to 0. So if you're saying, I want my spring mass system to quickly converge back to 0 after I've experienced a jolt, you're looking for the critically damped. That's your sweet spot. Now, what is that? Well, that's when you have repeated negative roots. So in other words, it's the same root twice. And of course, if it's repeated, we can have e to the minus at and e to the minus at. So our second one, we have to do a little bit of a bump. So that's where that t comes from. But in terms of the picture, it's really hard to tell pictorially the difference between critically damped versus overdamped. They don't look different. It is easy to see underdamped and undamped. One other quick thing we can talk about is we can actually sort of see ahead of time which situations we're in. Because we have the quadratic formula, right? And so our roots, if we just work them out, well, they're negative c plus or minus the square root of c squared minus 4mk all over 2m. So I'm applying the quadratic formula to that quadratic. And the behavior is going to be completely determined by what happens in there. That c squared minus 4mk. So, what do you want? Well, if we want this to be complex, which would be underdamping, what does it say about what's inside of this square root? It needs to be negative. So, underdamping, we can say, well, that's c squared minus 4mk is negative, or c squared is less than 4mk. If we want positive and, well, sorry, not positive. If we want two different real roots, what needs to be inside of our square root? It should be a positive number. So overdamping is basically going to be the opposite. So when c squared minus 4mk is positive, or c squared is above 4mk. Well, by process of sort of what fits in the middle, what's going to happen at your critical damping? Yeah, we need, if we want to have repeated roots, the part inside the square root has to be 0. So that says that c squared has to equal 4mk. So that's how we can quickly distinguish between the different possibilities. But as I said, it's going to come out once you see the roots. Once you see the roots, you know the behavior. It tells you everything. All right, well, let's try another problem. Okay. A mass spring dashpot, just remember that's just another way, a fancy way, if you will, to say damper, with no external force is being set up, which has a mass m of 4, a spring with spring constant k of 9, and a dashpot, damper, which has an adjustable damper constancy. So this is it's fancy. We can somehow set it at just the right level, our damper here. So wanting to maximize the speed the system returns to 0 after a jolt, it has been determined C should be set so the system is critically damped. All right, good. So, part A, determine C. Well, let's talk about what's going on. So, in general, we have a spring system, so we know it's mx double prime, cx prime, kx equals 0, mass, damper, spring constant. We know what the mck represent. We also know some of these values. So mass is 4, because it says it. Spring constant is 9, because it says it there. And the damper, we don't know. We get to pick it. All right, well, how do we go about finding that just right setting? What do we do? Well, you know, if we can go through what we just talked about. Of course, if we're not good at memorizing stuff, we say, well, let's just find out what would happen in the corresponding algebra problem. We know critical damping means repeated roots. So we know we want this to be a perfect square. Now, we can throw this into the quadratic formula. We can try to complete the square. There's all sorts of things we can do. But we say, aha, our goal, or maybe we should say we're thinking to ourselves, a perfect square. Yep. Simple thoughts. All right. So, well, so we'll go ahead and just work it out. Negative c plus or minus the square root c squared minus 4 times a times c, 4 times 9 is, yeah, big number. I don't know. 144? Sure, I'll buy that. All over 8. Yeah, it is 144. All right. So we see this, aha, we know repeated roots. We want the inside to be thing inside the square root needs to be 0. So we say that tells us that c squared needs to equal 144. So c has to be 12. Good. So we're done with part A. Now you might say, what about negative 12? Well, our damper constant is a positive thing, not a negative thing. If you have a damper constant which is negative, you're going to have a bad day, because it's going to basically blow up if you let it run for a while. You can try it out. All right. Now part B. Determine the general form for solutions using the answer from part A. But actually we can use our information, right? Because we almost have our roots. So we know that that part is 0. So, and we now know C. So we say, aha, R is negative 12 over 8. And it's actually a repeated root. Well, 12 over 8, there's a nicer way to write that. What can we call that? 3 over 2, because they both have factors of 4. Okay, so now we have that, so we can say, hey, our answer for B would be x equals some constant, e to the minus 3/2 t, plus some other constant times t, because it's a repeated root, so you have to have the second one bumping up, times t. So there's B. All right. So far, so good. We've knocked out 2/3 of the problem. Then we get to part C. Find the particular solution with x of 0 equals 3 and v of 0 equals 5. All right. Well, we already have x. Now v, we know is the derivative. So we'll write x prime. So that would be negative 3/2 a e to negative 3/2 t. Here, well, product rule, it'd be b times 1 times e to negative 3/2 t, and then minus 3/2 b t e to the minus 3/2 t. So here, took the derivative of t times the exponential. Here I left the t alone, but times it by the derivative of the exponential. All right, when we plug in x of 0, what comes out? Three, because it says. What else comes out? Oh yeah, A, sure, yeah. It's a A, yeah. Because this part goes away, because there's a 0 right there. So you get 0 times stuff, 0, our good old friend. So we know A. Okay, let's plug in x prime of 0. That's also v0, which is 5. All right, when we plug 0 into here, what do we get? Well, what's this part? Negative 3/2 a. How about this part? It's b. How about this last part? 0. Great. Okay, so we know a equals 3, and then we can say, that tells us that b has to be 5 plus, because when we bring over, it's going to become a plus 3/2 times a, which is 3/2 times 3. Well, all right. So 3/2 times 3 is 9/2. 5 plus 9/2, also known as 19/2. And so we know A, we know B, so our answer for C will be A e to the minus 3/2 t plus B 19/2 t e to the minus 3/2 t. Just to show I planned well, I got the right size. That's a t, I want you to know, my boxes are always the right size. So, all right, now, just to make you nervous, I'm going to put this up, and then I'm going to tell you, don't worry about it. So, like, oh my gosh, Steve, and then I'm like, don't worry about it. Okay. But this is just trig stuff. And it turns out, fun fact, that if you ever have something that looks like c cosine bt plus d sine bt, it can always be rewritten as a times cosine of bt minus theta. And there's various rules for doing it. All of this comes from basic trigonometry, and there's names attached to it. So you need to know what these things are in case it asks you for your homework. I don't care to test you on this, because this is not the point of our class. But that's all I want to say about that.